Now that we have discussed the curl, we move to discuss one of the most important theorems in electromagnetics, which is called Stokes Theorem. And this theorem is very useful because it helps us in converting surface integrals into line integrals and the other way around. So the idea of this theorem is very simple. Say if you do an integral of any vector around any closed contour, so you do a line integral all around this closed contour, you integrate h dot dl. We call it h here, doesn't matter. It's the name of the vector. You try to get its circulation around this closed contour. This is equivalent to integrating the curl of h over any surface S enclosed by that contour while observing the right hand rule. What does this mean? You could see here this the way the circulation is being done will give you the normal in the shown direction here, in the direction the normal ds. So the right hand rule still applies. So if you circulate in this direction, you will see that the normal will be in this case out from the page as shown here. So if this is your direction of integration, this will be your direction for the area. Okay, so this was you have to agree on, because at every point on the area element there are two directions of normal, either this one or the other one pointing downward. Now there are infinite number of surfaces enclosed by any contour. For example, if I take a circle, this is a contour here, correct? It's a contour. I can have this surface. This is surface enclosed by that contour. Maybe it's a surface with a hemisphere, or I can have this one as well, or I can have this one, or I can have any curved surface. These are 3D surfaces. Okay, so there are infinite number of surfaces, and for all of them, this theorem will apply. So the great thing about Stokes theorem is that it converts an integral over a closed contour to an integral over the surface, any surface enclosed by that contour. But you have to observe the right hand rule. If dl is circulating in a certain direction, this will be the direction of the rotation of right hand screw. Then ds is the direction of the progress of that right hand screw. We have to keep this one in mind. Where did this theorem come from? Well, the derivation is very simple, and here I borrow the derivation from the book of Skander. So if you want to calculate the integral of h dot dl around this closed contour here, so we build a closed contour around this surface. So as you can see here, I'm drawing a closed contour, and say I want to carry out the integral of h dot dl around that closed contour here. This closed contour encloses a surface. So what we do, we divide this surface into tiny elements, as you could see here. Each one of them has a square shape more or less. And then we start from the basic definition of a curl. If this is one of these elements, this is the ith element here. This is the ith element. And this is the normal to the ith element n. Then we can simply say from the definition of the curl at the center of that element. So at the center here we can say that the component of the curl normal to that surface is given by that expression. Where did this come from? We know that the curl normal to any plane at a point, we obtain it by creating very tiny contour around that point, carrying out the line integral as shown here, the closed line integral, and then dividing by the area of that tiny element, and then we try to make this element as small as possible. So what does this give us? This will give us the component of the curl normal to that surface. This is why I take dot product with n, where n is the unit normal. So if the element is already small enough, I will simply get rid of this limit and say, okay, this should hold fine, the element is small enough, and then I multiply both sides by delta SI. Delta SI is the area of the ith element of that surface. So when you multiply delta SI by the unit normal, you get the vector delta SI, which is really the differential area of that element. So what we did here, we said that the circulation around the ith tiny contour that we have is equal to curl F at that point dot delta SI, which is really the vector area or the area vector of that element. Now, if we do the same, we wrote this only as one at one of these elements, the ith element, but there is element 1, element 2, element 3, 4, 5, and so on. There may be a huge number of them. So what we do, we sum this over all elements and see what will be the result. One thing to notice here is that if you take a look at any two neighboring elements, for example, this is the ith element, if you take a look at the neighboring elements, you notice something very interesting, that this edge is integrated downward, this edge is integrating upward. So this common edge that, let me try to point at that now. This common edge that is joined by both of them, so this common edge shown here that is joined by both of them, the line integral over this edge in the first one, second one will cancel. Why? Because here I'm integrating f dot dl and it's pointing downward. This is the direction of the contour. And here I'm integrating f dot dl and this is the direction of my contour. So they end up cancelling each other out at this element. And this actually will happen for any internal element that's joined between two contours. So all these will cancel out. The only thing that will remain are the contribution coming from the external contour, because these are not shared between any two elements. So if you do the summation, this is what we'll end up having. So what we do here, we go back to this expression, we sum over all elements here, we sum over all elements here, and we notice that the internal contribution coming from the edges shared by any two elements will cancel out, and they end up only here with f dot dl over the external elements surrounding the whole area. This is what you do. As you said, I will integrate over all these contour elements or tiny elements here. These ones, as we agreed, all shared elements will cancel out. We are left only with f dot dl over the external contour, which becomes a closed line integral over the external contour. Here, if you take the limit as the number of elements goes to infinity, this becomes the integral of curl f dot ds. So we are integrating curl f over the surface enclosed by s, of course, after observing the right-hand rule. So the great thing about Stokes theorem is as follows. It helps you convert a line integral over a closed contour to a surface integral over the area enclosed by that contour while observing the right-hand rule. The direction of rotation of dl will be the direction of rotation of the right-hand screw. The direction of ds is the direction of progress of the right-hand screw. Now let's take a look at an example on how to apply Stokes theorem. We have here a function b, which is given in terms of its component. The z component has only one component here, which is az. Okay, and the az is a function of phi and rho. It doesn't have a z component. We want to verify Stokes theorem for a segment of a cylindrical surface given by rho equal to 2. So the cylinder has the radius 2, phi between pi over 3 and pi over 2. So it's a segment, and z between 0 and 3. We would like to show that indeed Stokes theorem will apply. Remember, Stokes theorem relates the integral over a closed contour to integral over a surface enclosed by that contour. This is very important to keep in mind. So if we draw the surface we are really trying to do the integration at, this is a cylinder, this is a cylinder of radius rho equal to 2. Here phi is equal to pi over 3, phi is equal to pi over 2 is the y-axis, z equal to 0 is the xy plane, z equal to 3 is this one here, this plane. So there is the contour really, or the area enclosed by all this, is this one here. So I'm going over it. As you could see, this area, I already baked the direction of that contour. So I baked the direction. So this will be the direction of my integration. Okay, and because I baked this direction, if you see where will be the direction of the right hand screw, it will be pointing in the rho direction. Okay, so I know two things. When I do the integral f dot dl, the integration will have 4 segments. The first one is over this one here, where phi is changing from pi over 2 to pi over 3. The second one is from here to here, is when z is changing from 0 to 3 while keeping the 2 other coordinates fixed. The third one is from here to here, when phi is changing from pi over 3 to pi over 2, keeping rho and z fixed. The last one is this one here, when z goes from 0 to 3. And because I baked this direction of rotation and observing the right hand rule, I know that the direction of my area is going to be in the rho direction. So now we have to do things. We have to do two things. First, we have to get the curl of the function b and integrate it over this area. Integrate over this area here. And as we explained earlier, for this area, the unit area here, differential area here, has the dimensions. This one here is rho d phi. This one here is dz, and this is all in the rho direction. So the area is rho d phi dz in the rho direction. For this one here, for this contour, we have to do out a contour integral as well, or line integral. Here it is rho d phi. This your element is rho d phi, and phi is changing from pi over 2 to pi over 3. Here dl is equal to dz, and z is changing from 3 to 0. And word of warning, don't say that dz is equal to or dl is equal to minus dz, and then you integrate again from 3 to 0. This means you are taking the negative sign 2 times. dl over this contour going from here to here is equal to dz, but the bounds are from 3 to 0. It's very important to understand this. The last segment is this one here. Here again, your dl is equal to rho d phi, and phi is going from pi over 3 to pi over 2 here. The last segment is this segment here, when dl is equal to dz, and z is going from 0 to 3. So now let's go how this is going to be translated, or this understanding is going to be translated into actual implementation. We start first by writing the expression for the curl. The curl for spherical coordinates is pretty complicated, but luckily we have only one component here for the vector b, which is bz. So as you can see here, this one here will cancel out because we don't have b phi, we don't have b rho. This one will cancel out, there is no b rho. This one will cancel out, there is no b phi. And we know as well, so the only two terms that will remain is really this term here, 1 over rho partial bz partial phi in the rho direction. And the second one that will remain is this one here, minus partial bz partial rho in the phi direction. Now if you substitute, the derivative of cosine will give you minus sine, so you end up minus sine phi. And remember, we divide by another rho, so you get here, oops. So what you get here, you get rho squared. So you get here rho squared in the denominator in the rho direction. And the second one, you differentiate the sine becomes minus cosine. So you end up here with this. Actually, this one here is a derivative related to rho. So you differentiate 1 over rho, it gives you minus 1 over rho squared, which is 1 we have here, and the cosine is the same. So here we differentiated phi, here we differentiated rho, here we divide by 1 over rho. This is what you end up having. The next step, of course, in this part, is to integrate this function, this curl here. You integrate it over the area, over the whole area, whose differential element is rho d phi dz in the rho direction. We carry now our integration again, as I explained earlier in the beginning. For this cylindrical surface, ds is rho d phi dz in the rho direction, and you should notice that I observed the right hand rule because the unit normal is a rho. So this our integral here, this one will be dot ds. ds has only a rho component, so only we need the curl component in the rho direction, which was minus sine phi over rho squared. So now we'll be integrating minus sine phi over rho squared, rho d phi over the area of the cylinder. Remember that rho is a constant. Rho is equal to 2, so rho will cancel with rho squared. You are left up with only one rho in the denominator, so this will give you 2 here. So you are integrating sine phi between pi over 3 to pi over 2. You are integrating z between 0 and 3 to cover the whole area of that cylindrical strip. So the integration of sine phi will give you minus cosine phi as shown here. You put the upper limit minus the lower limit. I here integrated dz directly because the integral of dz is z from 0 to 3 will give you 3, so I multiply by 3 immediately. Cosine pi over 2 will give you 0. Cosine pi over 3 will give you 1/2. So this, the result of this whole thing will be 1/2 multiplied by minus 3 over 2, so you get minus 3 over 4. So the integral of the curl over the surface enclosed by the contour is minus 3 over 4. What remains is now to carry out the integral of b dot dl over the closed contour that we talked about before. And just to remind you, this is how the contour looked like. We said we're going to select it this way. Um, so you can see phi changes here. This is the phi direction. Phi changes here. Z changes here. Z changes here. One thing to notice, so we have to carry out 4 integrals, L1, L2, L3, and L4. Notice that B has only a Z component, so that B dot dl over this segment will give you 0, because this segment is in the phi direction. It's actually dl here is rho d phi in the phi direction. So this term, this integral will give you 0. The same thing will happen for the third integral, which is this one here, because you are going from phi equal to pi over 3 to phi equal to pi over 2. Again, your segment is equal to rho d phi a phi, so this will give you 0. The last two terms is this one, and this one will be carried out along z. One of them 0 from z from 3 to 0. The other one z is between 0 and 3. And in both of them, dl is equal to dz az. Don't say it is minus dz az, otherwise you'll be taking the negative sign into account twice. This is what we do over the first segment. You are integrating the z component dot dz az from 0 to 3, and of course you are integrating over a line that is a vertical line. Rho is constant along that line is equal to 2, phi is constant is equal to pi over 3. And then you have a second integral, which is another vertical line where z is increasing from 0 to 3. This is again your z component dot dz az, but along here rho is equal to 2, phi is pi over 2. Luckily, the cosine of pi over 2 is 0, so this integral will give you 0. This integral will cancel out. You are left only with this integral. Cosine pi over 3 will give you 1/2, and rho is equal to 1/2, so these two will give you 1 over 4. The integral of dz between 3 and 0 will give you -3, and the answer is equal to -3 over 4, which is exactly the same result that we got using the surface integral. So what this is telling us, that you can verify Stokes theorem for any surface, for any contour, as long as the contour is enclosing the surface and you are observing the right hand rule of the selection of the direction of the contour and of the surface. I wanted to show you one more example here on how to apply Stokes theorem. So we have here a function f, this is in Cartesian coordinates, a function f which has only a constant x component and a y component, which is function of z and y squared. And we would like to verify Stokes theorem over this contour. So the contour is set for you. You can see here we are going in the clockwise direction in the yz plane. And remember, if you are going in the clockwise direction in the yz plane, then the direction of the normal to that contour is going into the beach. It's going into the beach, and this is the direction of minus x, because x is actually pointing out from the beach. So you have to be very careful. So your ds here, the ds over this element, if you want to draw a unit area here, so this one is dy, this one here is dz, but the normal is pointing into the beach. It's pointing into the beach. It's the minus x direction. So we can do that. Of course, we can carry out first the line integral over these 4 segments. Remember, y will go from 1 to 0 first. Here, dl is equal to dy ay, but you are integrating from 1 to 0. Here, in this second segment, dl is equal to dz az, and z will go from 0 to 1. Over this segment, dl is equal to dy ay, and y will go from 0 to 1. In the last segment, which is this one here, dl is equal to dz az, and z will go from 1 to 0. Very important to observe this. Now let's apply Stokes theorem. Let's see the result that we are going to be getting. Of course, you should start first by writing the complete expression for the curl. Very complicated, but luckily here, ax the x component is a constant, so there is no derivative relative to y, no derivative relative to z. Okay. And the second other component here is, maybe just to go back. And the second component that we have here is the y component, and the y component is function of y and z. So partial fy partial x will give you 0. You'll have partial fy partial z, and there is no partial fy partial y. So you have only one component that remained, is minus partial fy partial z in the x direction, and because fy is equal to zy squared, this will give you minus y squared in the x direction. So this is the only component that will survive. We know from our selection of the direction of the contour that our unit area, a differential area element, is minus dy dz ax. And notice why I selected the negative sign, because the direction of circulation of the contour and in order to observe the right hand rule. So what we do next is simply to integrate over the surface of this square minus y squared ax dot minus what dy dz ax. Remember, y will go from 0 to 1. We are integrating over the area. Z from 0 to 1. So we are integrating y squared dy dz. You give you y cubed over 3. You put upper limit minus lower limit. You end up getting 1/3 here. The integral of z dz will give you z between 0 and 1. You end up with 1. The second part that we have to carry out, which is the left hand side of Stokes theorem, we have to integrate over the closed contour of f dot dl, and as I explained earlier, we have 4 segments. First, we'll go over dl is equal to dy ay, and y is decreasing from 1 to 0. And the second one is dl is equal to dz az between 0 to 1. The third one is between y will increase from 0 to 1, and here dl is equal to dy ay. The last one is z is decreasing from 1 to 0, and here you have the dl is equal to dz az. But remember, because the function does not have a z component, here f dot dl, when dl is in the z direction, will give you 0. So this one here is 0 dot dl. The same thing is happening here, because the function does not have a z component. This term will cancel out. You end up only with these two terms. Over this first segment, you are integrating relative to y, and z is a constant. And if you remember, maybe I can try to draw it for you here. We had two segments here. The first one is this one, the second one is this one. Here z is equal to 0. Z 0, while here z is equal to 1. So if you put z equal to 0 in this integral here, you get 0. So this one will cancel out. Here if you put z equal to 1, you end up with the integral of y squared, which gives you y cubed over 3. Both upper limit minus lower limit, you get 1 over 3. But this is exactly the same answer that we got from the surface integral. So this tells us that indeed Stokes theorem does hold, and we can verify it for any contour and for any surface, as long as the contour is enclosing the surface and we are observing the right hand rule in both cases.